Hello everyone, I welcome you all to Physics Wala, and in this session we are going to discuss the next portion related to our very interesting chapter, which is thermodynamics. And basically in this session we are going to understand some important properties, thermodynamic properties, and we are going to derive different type of relationships with respect to these type of properties. And this session is going to be very interesting because in this session we are going to practice a lots of questions. Okay, so let's start with the first part, what we are going to discuss in this particular session. So first part is we are going to discuss about the concept of internal energy. Then we are going to talk about the work done, how you are going to calculate work done with respect to a particular gas. Then we are going to discuss the most important part of this chapter, which is the first law of thermodynamics, as well as we are going to discuss about the concept of enthalpy. Now the main question is, we were talking about the concept of state function as well as path function. So how we are going to determine that particular part? If somebody asks you like how you are going to determine that this particular function is a path function or this particular function is a state function, how you are going to determine that particular part? So let's start with the first question. Question says that show that the volume of a fixed amount of an ideal gas is a state function, which is a very interesting question. Now basically in this particular case we have the relationship with respect to volume. We have to find out that volume is a state function or it's a path function for an ideal gas. That part we have to determine. Now in this case the main thing is, it's already given that we have a fixed amount of an ideal gas. So how to start these type of questions? So first of all, if I talk about the ideal gas, so in this case we have ideal gas equation. We can write down the ideal gas equation, and that ideal gas equation is a very easy, which is PV is equal to nRT. Now in this equation we know that P is the pressure of the gas, V is the volume occupied by the gas, N is basically the amount of substance or moles, whatever of gas we have taken. R is basically the universal gas constant, and T is the absolute temperature. Now how to proceed for these kind of questions? In this case it's already given that we are talking about the fixed amount of gas. If this part is given, I can simply say that N is basically constant. R, we already know that R is basically universal gas constant. It means in this case variables are basically volume, temperature as well as pressure. So if I talk about the formulation, I can write down that V will be equal to nRT by P. And from this particular part I know that these two are constant. It means we can say that volume is basically a function of pressure as well as temperature, because these are the things which are variable. Now I am going to use a very interesting concept, which is actually known as Euler's reciprocity. I'm going to use a simple calculation related to Euler's reciprocity. So let's say if I talk about a function which is, let's say, phi. This phi is a function of, let's say, x and y. So how to derive this entire portion? So according to this Euler's reciprocity, we can simply say that first part, which is d by dy, d phi by dx at constant y, and its double differentiation at constant x will be equal to d phi by dy at constant x, which is a double differentiation of x with respect to y. If this thing comes out as same, LHS is actually equals to RHS, then we can say that this reciprocity is going to work, and definitely in that case we can say that we are talking about the same analysis, that we are talking about the state function. I hope this part is clear. So you just have to apply this reciprocity, and then you will get to know if LHS is equal to RHS, and definitely that function is going to be a state function. Now in this case, phi is basically volume. It's a function of x and y. It means it's a function of pressure and temperature. So first thing what we can do, we can say that dV by, let's say, dt at constant pressure. Can I calculate this value? Yes, very easily. So that will be d by dt, then we have nRT by P, and the entire part is at constant pressure. Now in this case, if the pressure is constant, the only differentiation will be of T part. So I can say that this will be nR by P dP by dP. I can simply say that dt by dt, that will be dt by dt at constant P, and you know this entire part, this will be equal to nR by P. So we have calculated the first part. Now again in this case I can say that again differentiation of this entire part with respect to P, of which part we have dV by dt at constant P, entire differentiation with respect to constant T. So this quantity we have already calculated. Now we have to differentiate it with respect to P. So I can say that will be equal to d by dP nR by P at constant temperature. So we just have to solve this entire part. Now if I move this entire part to the upside, it will become P raised to the power minus 1, and differentiation we know that we have A raised to the power n, so that will be n, then A raised to the power whatever is given. So basically if I talk about the differentiation, I can write down the formula. So let's say we have a quantity which is x raised to the power n, and if I want to differentiate this entire part with respect to dx, so that will be equal to this n power goes down and x raised to the power n minus 1, that will be the differentiation. So if this becomes P raised to the power minus 1, then you will get to know that this value will be minus of nR P raised to the power minus 2, that will be P square. So that will looks like this, minus nR upon P raised to the power 2, that will be the final part. So first quantity is already being calculated. Now we have to work on the next part. I can say that we have to calculate dV by dP at constant T. So that will be d by dP of nRT by P at constant temperature. If the temperature is constant, I can say that will be equal to nRT, then d over dP P raised to the power minus 1. You can again solve this entire part. That will give you the value which is minus of nRT by P square. Now next part. In this case, again I am differentiating it with respect to dt. So that part will be dV by dP at constant temperature, and this entire part with constant pressure. So this quantity is already being calculated. So I just have to put the value. So that will be d by dt. Next part will be minus nRT by P square, and this entire part is at constant temperature, I can say. So what you can do? You can say that will be minus nR over P square dt by dt at constant pressure, So you know dt by dt is going to be 1 again. So that value will be minus nR over P square. Now just look at the value. This is minus nR over P square. Again the previous part was minus nR over P square. So you can simply say from that particular part that d by dt dV by dP at constant temperature and at constant pressure will be equal to d by dP dV by dt at constant pressure and entire part at constant temperature. These two things are actually equal, and that proves the Euler's reciprocity. So it means this particular function, which is we are talking about the volume part, I can simply say that for a fixed amount of an ideal gas, that volume is a state function. So that is true in this case. We can say from this particular part that volume is a state function. I hope this part is clear. Now you can try to solve this entire part for pressure also. So let's say for a fixed amount of gas, that pressure is a state function. Let's try to solve this entire part and let me know that what you are going to get in this final analysis. So the analysis is going to be same. You just have to apply Euler's reciprocity whenever you are talking about the state function calculation. So if this entire part, this entire theorem holds true, it means you are talking about the state function. I hope this entire part is clear to everyone. Now, let's move on to the next part. We are talking about the concept of heat capacity. It's a very simple analysis, although we are going to talk about the entire analysis part of heat capacity much more in the upcoming sessions, but it's a simple definition part. So basically, if I talk about the heat capacity, the amount of heat required to raise the temperature of a given amount of substance by 1 degree Celsius, that will be actually known as your heat capacity. And generally this heat capacity is shown by C. So in this case, this heat capacity is basically C, which is basically the heat requirement to increase the specific amount of substance by 1 degree Celsius. So that will be Q by delta T. So that is the first formula related to heat capacity. But again, you can define a specific heat capacity. You can define molar heat capacity just like the same analysis. So if I talk about the molar heat capacity, it means the amount of substance is now fixed. You are talking about the amount which is 1 mole. So basically the amount of heat required to raise the temperature of 1 mole of substance by 1 degree Celsius is actually known as a molar heat capacity. And in this case, you are going to determine that entire part by Cm. So in that case, Cm will be equal to whatever heat capacity divided by N, and that value will be equal to Q by N delta T. I hope this part is clear. So again, the heat capacity has almost same units just like the previous part, but in this case you are dividing the entire part with mole, so it becomes joule per mole per Kelvin, not joule per Kelvin only. And you can convert joule part into calorie, as well as you can convert the entire part into erg also. That depends upon the calculation whatever is given to you. Okay, so that is the basic analysis part. Now we have divided the entire part with mole, and I told you that whenever we are talking about any extensive property, if I divide that particular part with moles, definitely it will become an intensive property. So this molar heat capacity is an intensive property, while that heat capacity was an extensive property. Okay, now just like that, if I talk about the specific heat capacity, in this case I'm talking about the amount of 1 gram of substance by 1 degree Celsius. So in this case, you can say again we are talking about the CS part, which is a Cm, whatever mole capacity we are talking about, divided by the molecular weight. So it becomes like this, CS will be equal to Q upon M delta T. So that is the formulation. Don't worry, I am going to talk about this heat capacity part again in the upcoming sessions when it is actually required. Okay, now, okay, so we have one more question here. A piece of aluminum metal weighing 3 gram requires 5.4 joule of heat to raise the temperature from 298 to 300 Kelvin. So first of all, we can calculate delta T. Delta T will be 300 Kelvin minus 298. That will be 2 Kelvin only. So we have increased the amount of the temperature by 2 Kelvin. Now in this case, first of all, this W of aluminium is already given, which is 3 gram in this particular case. Okay, next part is 5.4 joule of heat is required. Basically, a piece of aluminum metal weighing 3 gram requires 5.4 joule of heat to raise the temperature from this amount to this amount. Okay, then find out the heat capacity, then molar heat capacity, then a specific heat capacity. Every part is already given to you. If 3 grams of aluminum are given, you can say that the number of moles of aluminum are basically 3 divided by 27, which is basically the molar mass or I can say atomic mass of aluminum. So that will be, I guess, 1 by 9. So you have calculated the amount of this part, which is 1 by 9 moles. You know that the heat in this case is 5.4 joule. So you can say Q value is already given, which is 5.4 joules. Now you can easily apply all the formulas to calculate whatever relevant quantity is required. Okay, so basically I am giving this question as your homework. Just let me know the answer in the comment box. Okay, you just have to apply the formula. I have given you entire hint related to the calculation part. You know the number of moles, you know the Q part, you know the delta T. So you just have to put these values and calculate the final answer. Okay, I hope this portion is clear to everyone. Very simple analysis, very easy question indeed. But in upcoming sessions, we are going to discuss more and more questions related to JEE mains as well as advanced part. Okay. Now, okay, so we have another question, which is a 5 mole of an ideal gas expand isothermally and irreversibly from a pressure of a 10 atm to 1 atm against a constant external pressure of 1 atm. W irreversible at 300 Kelvin is. Now the main question is, sir, we don't know about the calculation of work done. Sir, what is the calculation of work done? That part though we don't know. So let's try to find out like what is the actual calculation of work done. Then we can proceed for the calculation part, like how to solve this question. Because in case of work done, basically in cases of gases, we are talking about the PV work done and how to derive that part. If the process is isothermal, irreversible, everything is given. So how to understand this particular part? Because most of the students are already confused. Sir, the question is already very lengthy. Entire information is given. Now I don't know which information to pick and how to start the question. So it's very easy. Basically, we are going to talk about the calculation of work done first of all. Then we are going to proceed for the question analysis part. And then I'm going to give you certain tricks to understand the concept of work done and how you are going to determine that particular part. Okay, just a second. So let's start the work done calculation here only. Let's start the work done calculation here only. Okay, so okay, now it's good. So basically I'm going to talk about the calculation of work done. Now I'm going to talk about the calculation of work done. Basically, if we talk about the work done, generally we know that whatever work done is happening, dW is actually equals to force multiplied by slight displacement. According to physics, we simply say whenever we are applying a particular force and a certain amount of displacement is happening, in that case we can say we are talking about the work done. Okay, now in this case there is no discussion about the gases because we have to convert the entire part for gases. So how to understand that we are going towards the work done calculation of gases? So in that case, let's say we have a container. Let's try to draw a very interesting container. Okay, let's try to draw the container. So let's say this is your cylinder. Okay, this is your cylinder. And in that case, in this cylinder, there is a movable piston. There is a movable piston which is already there. There is a movable piston which is already there. Now, in this piston, let's consider that there is a gas. There is a gas which is present. Now, this gas is having pressure which is P. So it has a specific pressure which is P, and in that case the volume occupied by the gas is V. Okay, so P is the pressure of the gas, V is the volume occupied by the gas. Okay, that is the basic idea. Now in that case, let's say we are talking about some external pressure also, P external. We are talking about the external pressure which is P external. Now in this situation, there is a hypothetical concept. Let's say that the P internal part, if I talk about the P internal part, which is the pressure of the gas. Pressure of gas, let's say, is slightly greater than external pressure. Let's say that this pressure, whatever is the pressure of gas, it is slightly greater than the pressure of the external atmosphere, whatever is present. Let's say the area of this piston, cross-sectional area of this piston is basically A. This is the cross-sectional area. Okay, this is the cross-sectional area of the piston. Let's say if this amount of pressure of the gas is slightly greater than the external pressure, it means gas is going to expand. It means slight expansion is going to take place. Slight expansion is going to take place. Now, just because of this slight expansion, let's say earlier this this piston was on this position. Let's say earlier this piston was on this position. Just because of the slight work, it's going to go upward. And let's say in this case, this displacement, very slight displacement is, let's say, dl. This displacement is, let's say, dl. That is the first part. That is the first part. Now we know that if I talk about the pressure, pressure is basically force per unit area. That is the formula of pressure. So we know that pressure is actually equals to force per unit area. Area is the cross-sectional area of the piston because it is applying on the piston. Piston is going upward. So you can say that force in that case will be pressure multiplied by area. That is the first part. And that P is the P of gas, and they are moving in the same direction. They are moving in the same direction. So I can say in this particular case that this entire part will be rewritten as dW will be equal to pressure into area into dl. Okay, that is the first part. That is the first part. Now this is the P internal, that gas is expanding. If I'm converting that part in terms of P external, I can say the negative force of P external will be applying. So that becomes dW is equal to minus of P external multiplied by A into dl. That is the most important thing, because I am converting this P internal part in terms of P external. So that will be the negative part. If gas is expanding, it means that will be the opposite. It means you can say the pressure is applying like this and displacement is happening like this. So there is a bond angle which is 180 degree. And there is a formula which is corresponding to work done. If you are talking about the bond angle also, if you are including that particular part, that will be FDL multiplied by cos theta. In that case, cos theta is basically 180 degree. So you can say that minus sign also comes from that particular part. But easily you can understand that this pressure is basically P internal. If I am converting that part in terms of external pressure, I can say that will be minus of P external, because entire part is going against that external pressure. Now this is the first formula. Now I say if I talk about the volume change in that piston, volume change which is, let's say, dV, that will be equal to A is going to remain constant. So A will be there multiplied by slight displacement which is a dl. So you can convert this entire part like dW will be equal to minus a P external, that will be equal to dV. So this is the formula which is pretty much required. Now don't think that this minus sign corresponds to anything. The final value after the calculation corresponds to the compression as well as expansion part. Okay, just remember this thing. If I talk about this particular part, I can say that again I can divide this work done for two processes. First one is irreversible process and the next part is for reversible process. In the previous session, we were talking about the reversible as well as irreversible processes. Irreversible process always occurs at a constant external pressure and it's a fast change. You can say that entire part is going to change very fast. So in this case, I can say that dW will be equal to minus of a P external. Then we have dV. I can say the entire part we can take integration, and the volume is changing from V1 to V2 within limits. So we can integrate that particular part. Now again in this case, P external is constant. For irreversible process, always remember that pressure is not changing slightly. We know in that case that P external is going to be a constant value. So the entire work done is actually happening under a constant pressure. So in that case, you can say if this part is constant, so that will become that W, which is irreversible, will be equal to minus of P external as it is. Then we have a V1 to V2 dV, and this part will be minus of a P external V2 minus V1. That is the formulation. Now this entire process is happening at constant temperature. We are talking about at constant temperature, because we don't want so many confusions. We are talking about the PV work. If we are talking about the PV work, we need to consider that temperature is constant. Then only we can correlate pressure and volume, because otherwise we will have three different variables: pressure, volume and temperature. So this entire process is happening at a constant temperature. So at constant temperature means we are talking about the isothermal process. We are talking about the isothermal process. I hope this part is clear. Now in this case you can see W irreversible is very easy, which is minus P external V2 minus V1. That's it. That's it. Now how to deal with the reversible part in this case? That is the most important question. So again in this case we are talking about the isothermal process, and this process is basically reversible in nature. If this condition holds true, we know that in case of a reversible processes, we know that P external is basically equals to P internal plus minus dP. That depends upon the expansion as well as compression. Now one more thing which I want to add. So how you can say that this work done is expansion work done or compression work done? So if this entire part holds true, I can say that W irreversible will be equal to minus P external V2 minus V1. That was the part. Now let's say that V2 is greater than V1. If V2 is greater than V1, means after the entire application of pressure, volume is increasing. It means we are talking about the process of expansion. We are talking about the process of expansion. Now if this holds true, so we can say V2 minus V1 will be a negative term itself. Sorry, V2 minus V1 will be a positive term itself, and the entire part, positive part, when multiplied with negative, then we can say that W irreversible in that case will be negative. I hope this part is clear. It means in case of expansion, work is done by the system, and when the work is already done by the system, it's always negative. This is the first part. This is the first part. Now the second part, in this case you can say if V2 is less than V1, it means earlier the volume was more, but now the volume is less. It means we are talking about the process of compression. Now in case of compression, you know that this V2 minus V1 will be a negative term. If this is already negative, negative multiplied by negative, then we know that W irreversible in that case will be positive. So for compression part, you have to work on the system. So this is by the system, and this is on the system. I hope this part is clear. In the previous class, we were only talking about the sign convention, why it is negative, why it is positive, but now we can see that this entire part holds true. I hope this portion is clear. Now let's talk about the next portion. In case of reversible processes, in case of isothermal as well as reversible processes, we know that external pressure is slightly greater or less than the internal pressure. So I can replace the equation. We know that dW will be equal to minus of P internal plus minus dP, then we have dV. Okay, and let's try to integrate it. Let's try to integrate it from V1 to V2. If that holds true, it means we have a minus P internal dV, then we have a plus minus of this entire part. So that will be minus of a P internal, then we have dV from V1 to V2, and we have minus plus dP dV from V1 to V2. Now we know dV is a small change in volume, dP, which is already a very small change in comparison to the external pressure. So this dP and dV, this is going to be very small quantity. Whatever it is, it's going to be very small. If it is very small, if it's going to be very small, then we can neglect this part. We can actually neglect this entire part, and the final equation becomes like this, which is minus of V1 to V2 P internal dV. Now I'm not saying that P internal is going to be a constant one, because this is the pressure of that ideal gas which is present. So let's say we are talking about the ideal gas. So for ideal gas, that P will be equal to nRT by V. So can I put this value? Yes, definitely. That will becomes like integration within the limits of V1 to V2. Then we have nRT by V dV. Now we are talking about the isothermal process. It means temperature is constant, R is already constant, number of moles of gas in that particular scenario is going to be remain constant. So we can say that will become minus of nRT. Then we have a V1 to V2 dV by V. And we know this integration is basically ln V, ln of a V. So that will become minus nRT. Then we have ln of V within the limits of V1 to V2. And finally we can say the formula will be minus nRT ln V2 over V1. That will be the final formula. I hope this entire part is clear. I hope this entire part is clear. So that is the first analysis you can do for this calculation. Is there any other way you can expand this formula? Yes, we have. Yes, we have. So W reversible in case of isothermal process is basically equals to, so that will be minus of nRT ln V2 over V1, because that was ln V2 minus ln V1. So that is ln V2 over V1. So I am writing this directly. Now in this case you can also write down the formula, which is minus 2.303 nRT log V2 over V1. You can also write down the formula like this, which is W reversible. This is the first formula for the reversible part. Is there any other way you can convert this entire part? So yes, for constant number of moles, constant temperature, we can say that we have a relation which is PV is equal to constant at constant temperature and amount of substance. We know this particular part. It means P1 V1 will be equal to P2 V2. If that holds true, we can say that V2 over V1 will be equal to P1 over P2. Yes, definitely. So I can put this value, and W reversible in that case will be equal to minus 2.303 nRT. Then we have log of P1 over P2. That formula is also true when you are going to apply, when you have the value of a pressure only instead of a volume, then you can use this formula also. Okay, I hope this entire part is clear to everyone. So let's say if I talk about the process of expansion, let's say we are talking about the process of expansion, which is P versus V in this case. Okay, process of expansion means starting point is this and end point is like this. Now in this particular scenario, you know that at every time, if I'm talking about the reversible work done, at every time this entire part is slightly changing, the pressure is slightly decreasing. So let's say it starts from this part, and it actually ends to this particular part. Now in this case the pressure was this. In this scenario, let's say the pressure is this. But you know, in case of reversible process, the process is occurring in infinite number of steps. Means it's going to go on this side, eventually it's going to go on this side, eventually it will move on this side and this side, this side. You just have to include everything. You just have to include, because the process is occurring in infinite number of steps. This is I'm talking about for the reversible reaction, that the process is occurring at multiple steps. The process is occurring at multiple steps. The process is occurring at multiple steps. This is the basic idea. Now in this particular case, if the process is occurring at every moment and you are integrating the entire part, what does it mean? It simply means you have to include this entire portion. You have to include this entire portion. You have to include this entire portion, because every time this entire part is changing. It means this area under the curve corresponds to the W reversible part. This corresponds to the W reversible part for expansion. and it looks like that the area under the curve is actually very, very large, because the steps are infinite, and every time you have a specific area under the curve and you just have to integrate the entire part and you will get this entire portion. This is the basic analysis. Now this scenario is not same in case of irreversible processes, because in case of irreversible process, let's say again I have this pressure and volume curve. This is pressure and this is volume. So starting point was this. Again we have the expansion part. So earlier the pressure was this initially. So let's say this is P1 and V1 and in this case the final part is basically P2 and V2. Okay, and V2 will be like this only. Now this entire part is working under the external pressure. So I am saying that the P external is basically equals to P2. So the entire part is actually happening under the external pressure of P2. It means now you cannot include this entire part, because in this case this entire analysis of expansion is happening under a constant external pressure which is equals to P2. So if P2 is like this, this is your P2, this is your P1, and this is your V2, this is your V1. It means you just have to include this entire part. You can include only this part, because the entire work is happening under this constant pressure only from V1 to V2. Now you can see this area under the curve and the previous area under the curve. Which one is more? You can say, sir, this is very, very large. This area under the under the curve is actually very, very large, which is a multiplication of P and V. Work done, you can say. So in this case, this W of irreversible in case of expansion is actually much less in comparison to the reversible part. I hope this graph is clear to everyone. This is a very important graph, and most of the students are already very confused, like what is the meaning of this entire part. So in this case you are only talking about the work done under a constant pressure. It means this area under the curve talks about that work done. But in this case the process is occurring at infinite number of steps. You have to integrate the entire part and combine the entire area. So that becomes this large area, which is the area under the curve. That is work done. So reversible expansion work done is always greater than the irreversible part. I hope this portion is clear. I hope the entire calculation is also clear to everyone. Now let's talk about the question. So first of all, isothermal is given, irreversible work done is given. So in this case, pressure is from 10 atm to 1 atm against a constant external pressure of 1 atm. Okay. So N is given, which is 5 moles. We know that this entire part is already constant. Now in this case, a temperature is 300 Kelvin, which is again constant. Isothermal process is there. Now P1 is basically 10 atm and P2 is basically 1 atm and P external is also equals to P2, which is 1 atm given in the question. Now the main source of confusion, sir, in this case only pressure is given and you have calculated the formula of W for reversible process in terms of pressure, but we don't know any formula for volume, because in case of this particular part, which is your irreversible work done, there is only one thing, which is P external V2 minus V1, and there is no relation of V2 and V1 with the corresponding pressure. So how to do this particular question? That is a genuine question. Like in this case, if I talk about the W irreversible part, I know that this particular part is minus P external V2 minus V1. Now in this question, V2 and V1 are missing, only P1 and P2 are given. So you have the information of P1 and P2, you have the information about N, you have the information about T. Can you apply the ideal gas equation? Yes, if you can apply the ideal gas equation, you know that V will be equal to nRT by P. That is the first part, using the ideal gas equation. If that's true, then I can say that V1 will be equal to nRT, because everything is constant, nRT by P1, and V2 will be nRT by P2. So can you put the values? Yes, definitely. So we can say that will be minus of P external. then we have nRT upon P2 minus nRT upon P1. So we can say that will be equal to minus of P external nRT, then we have 1 upon P2 minus 1 upon P1. If I am again using the entire calculation, I can say that will be minus of nRT, then we have P external upon P2 minus P external upon P1. Now you know that P external and P2 are exactly same. If they are same, then this entire part will be equals to 1. So the final equation becomes like this, which is minus of nRT 1 minus P external upon P1. So what you have to do, you just have to put the values and calculate the final answer. Answer is in kilojoules, so you need to make sure that R value is 8.314. Now let's try to solve it. So basically W irreversible in that case. So let's take another page. So W irreversible will be minus of nRT. Then we have 1 minus P external upon P1. That's the part. So I can say minus of 5 multiplied by 8.314 multiplied by 300. Then we have 1 minus, that will be, I guess, P2 is 1 or P external is 1 and P1 is 10. So that will be 1 upon 10. So that becomes minus 5. This is minus 1500 multiplied by 8.314 multiplied by, we have 9 by 10. So this is going to cancel out, this is 0. Then that will be minus of 1350 multiplied by 8.314. So we just have to solve this entire part. Minus 1350 multiplied by 8.314. Okay, and you will get your answer. I guess that will be 11.224 kilojoule per mole. Okay, that will be, I guess, option B. I'm not sure, but you can solve it by yourself. Just let me know. That value is in joule currently. That value is in joules, but you can convert the entire part into kilojoule also. Okay, so that will be your homework. I hope the calculation part is clear. I hope the calculation of work done is clear to everyone. Just have a look at it. Okay, now this entire part is clear. Now we can move to the next part. So we have calculated the entire portion related to the work done part for PV work done only. Now it's time to talk about the next portion, which is internal energy. And remember, internal energy is basically, we are talking about the system. System is anything. Let's say you are talking about a particular gas. So internal energy is basically the sum of different type of energies which are associated with the atoms or molecules which are present in the system. So I can say it can be your electronic energy, it can be your nuclear energy, it can be chemical bond energy, it can be potential energy, or it can be kinetic energy. In terms of kinetic energy, again you have different type of modes. It can be translation energy, it can be vibration energy or vibrational energy, or it can be your I can say rotational energy. So there are different modes. Every type of system contains a specific amount of energy. So in that case, this internal energy is U, which is a summation of these types. You can say U kinetic energy plus U potential energy plus U nuclear energy plus U bond energy, whatever it is present, whatever type of energy is present, you can say that is the internal energy of the system. So a specific amount of energy is always associated with a particular system. That energy is actually known as your internal energy. Again, we know certain things about internal energy. We say that this internal energy is an extensive property. This is an extensive property. But if I talk about this particular part, it's a state function. Okay. it doesn't depend upon the path taken, but the value of this entire part is going to be always constant. Now remember, whenever we talk about this entire part, we know that the exact calculation of u is not possible. You cannot talk about the exact calculation of u, definitely, because it is associated with different amount of energy. You cannot talk about each and every part of energy very specifically. So it's better in this case, it's better to calculate change in internal energy. Always remember, in this case, the change in internal energy is always possible, and that's why that entire part is a state function, because that change is not depending upon the path taken. Whatever path you have taken, it always depends upon the initial as well as final state. So that is the basic idea about the internal energy. You can say that change in internal energy can be calculated by, but the absolute value of this entire part cannot be calculated. So this change will be final state minus initial state internal energy. It can be anything, like whatever you have provided. And how you can change this internal energy, that is the most important question. Sir, we are talking about the change. So let's say initial state is, let's say u1. The internal energy of the system is u1 or ui. Now, how can you change this entire part? So there are certain methods by which you can change the internal energy. Either you can provide heat or you can absorb heat from the system. It means heat is given to the system and heat is extracted out from the system. Then you can change the internal energy. Or work is done on the system and by the system. In that case, you can definitely change the internal energy. Or if certain amount of matter leaves or enter to the system, definitely internal energy is going to change. That's why it is a extensive property, because it depends upon the amount also. So by these three methods, you can actually change the internal energy. I hope this entire part is clear to everyone. I hope this entire part is clear to everyone. We know that it's a state function. It means it depends upon the state of the system and independent of the method by which the state has been achieved. So it doesn't depend upon that particular part. In the same way, you can say it's an extensive property, because it depends upon the amount. It depends upon the quantity of the substance containing in the system. So if you are changing the matter in and out, definitely this internal energy is going to change, because in that case, certain amount which corresponds to rotational or vibrational or kinetic energy or potential energy, that part is going to change. So internal energy is going to change definitely. That's why it is an extensive property. This is the basic idea about the internal energy. But I haven't talked about the calculation yet, like how to deal with the calculation of internal energy. Now it may be possible that initially the internal energy was more, and after certain changes, whatever it is, work done change, heat change, matter change, whatever it is, that the final internal energy becomes less. It means that delta U will be negative in that case. If the final internal energy is more, then you can say that delta U will be positive. That's it. That is a basic idea related to the entire analysis part. Now, the thing is, which is the most interesting thing in this case, generally we say that this change in internal energy, or we can say, if I talk about the internal energy, generally it's basically the potential energy as well as kinetic energy. Generally we say that this entire part is potential plus kinetic energy. That is the basic analysis part. If that's the situation, I can say that change in internal energy will also be the change in potential energy as well as change in kinetic energy. That's the next part in this case. And always remember that this kinetic energy always depends upon temperature only. The kinetic energy always depends upon temperature. Just remember the kinetic theory of gas, which simply says that average kinetic energy depends upon the absolute temperature. So this depends upon temperature only. But this potential energy depends upon the pressure, volume, temperature as well as amount of substance. It generally depends upon everything. Now, generally in this entire analysis of thermodynamics, we are going to talk about the PV, work done. We are going to talk about the gases only. So let's start with the first part. In case of gases, generally we know that U is basically a function of a temperature as well as volume only. Generally we say, because it corresponds to both these parts, temperature is always there, but generally in this case we are talking about the temperature as well as volume. It means I can say that du will be equal to du over dv at constant t plus du over dt at constant v. You just have to understand how to derive these type of relationships. So if something is a function of temperature and volume, it means the change in that particular part corresponds to change in volume at constant temperature and change in temperature at constant volume. Now you can expand, you can expand this entire part. It will be like this: du will be equal to du over dt at constant volume and then differential with respect to dt plus du over dv at constant temperature then dv. So you just have to understand, you can write down this type of expression if something is a function of temperature and pressure, or pressure and volume, or you can say temperature and pressure. So that's how you can write. We are going to derive these type of relationship for enthalpy also, for Gibbs free energy also, and if possible we will try to derive some relationship for Helmholtz energy also. Okay, so this is the first expression. Now there is a specific term which is related to the change in internal energy with respect to temperature. This entire part is actually known as heat capacity at constant volume. This part is known as heat capacity at constant volume. We are going to derive that formula also, but just for now, just understand that this du by dt at constant v is basically heat capacity at constant volume. So I can say this will be du will be equal to Cv dt plus du by dv at constant t. This is the entire part. Okay, this is the entire part. I hope up to this portion everything is clear to everyone. Up to this point everything is clear to everyone. Now this is the expression for general cases of gases. Now consider, in case of ideal gas, ideal gases have no force of attraction between gases. They have no force of attraction between the gases, which is the kinetic theory of gas, which simply says that gas molecules are very far apart and there is no force of attraction, there is no force of repulsion between the gases. If that part holds true, it means this entire part will be zero. In case of ideal gases, this entire part, the change in internal energy is not going to depend upon potential energy. This entire part will be zero. It only depends upon the kinetic energy. If that holds true, it means you are differentiating this entire part, because in this case you are talking about the ideal gases and they don't have anything related to potential energy part. It means you are differentiating a constant value because it only depends upon temperature. In this case volume is changing, so volume is changing, it's not going to change anything. It means this entire part becomes zero in case of ideal gases. This is the only thing which you have to understand. So this du will become only one thing, which is NCVM dt. CVM is the molar heat capacity at constant volume. Now the last thing which I want to give to you, which is for isothermal process. In case of isothermal process, always remember that du will be equal to 0. Why? For isothermal process, in case of ideal gas, this part, potential energy part, was also 0 because it depends upon temperature only and you are changing volume, so it's not going to change the internal energy. So that part, that differentiation is 0 because differentiation of a constant term is not going to give you any value. Okay, so that part is removed. So the remaining equation becomes NCVM dt, or you can say CV dt. CV dt is NCVM. So that is NCVM dt. Now at constant temperature, isothermal process means in this case dt is actually 0. So if this part becomes a 0 also, you can say that internal energy change in case of ideal gases for isothermal process will be 0. Just remember this thing. This is going to be very important one when we are going to derive the relationship of first law of thermodynamics. I hope this entire portion is clear, and that is the only calculation related to your internal energy. The same part we are going to do, we are going to perform for enthalpy also. Okay, so just have a look at it. Okay. Now coming back to the topic, now we have the understanding about the work done, how to calculate the work done. We have a specific idea about the heat also, and next part is internal energy. Now let's try to apply the entire part for first law of thermodynamics. But before that, one more thing I want to mention, although it's not that relevant, but it's important to discuss that part. Which is the 0th law of thermodynamics. So this law is very easy. It simply talks about the concept of thermal equilibrium. It only talks about the attainment of thermal equilibrium. So let's say I have a body which is A. Okay, this A body is in thermal equilibrium with another body which is C. Let's say there is another body which is B, and this B is also in thermal equilibrium with this same body which is C. So if two bodies which are A and B, they are in thermal equilibrium with another third body which is C, then definitely they are in thermal equilibrium with each other. That's the only thing. If they are in thermal equilibrium with the third body, definitely they are in thermal equilibrium with each other also. So for example, let's say I have a container in which a gas is present having a specific temperature. I have another gas having a specific amount and a specific temperature. Now let's say these two temperatures are exactly same, and when I connect these two parts with a wall of a container which is actually thermal conductor, I can see that there is no change in their temperature because both the temperature are same. They are in thermal equilibrium with each other, and you cannot see any type of change in their temperature. And you can like measure that temperature with the help of thermometer. So thermometer actually talks about the rise or fall of that mercury. It means it talks about the mercury column is always going to rise up to that part when it becomes in thermal equilibrium with the container, or what is the temperature of that material inside. So that's the basic idea. It becomes again in thermal equilibrium. So if you compare these two containers which are having same temperature and they are connected with each other, you can see there is no change in the temperature because they are already in the thermal equilibrium with each other. So that is the basic idea of the 0th law. It's important to understand the basic idea of 0th law so that we can actually understand the next part, how this temperature change is going to affect everything, how this temperature change is going to affect the part related to first law of thermodynamics, internal energy, heat of the system, work done of the system. That part we are going to understand. Okay, so that is the basic idea about the 0th law of thermodynamics. I hope this portion is clear. Now let's talk about the first law of thermodynamics. So I can say it's not a law, but it's a simple statement. It simply says that according to first law of thermodynamics, that energy can neither be created nor be destroyed. You can convert one part of the energy into another part. You can convert its form either in terms of your heat or in terms of work done. You can actually change that part. But if I talk about the entire energy of the universe, I can say there will be no change in the energy of the universe. Okay, so that is the basic idea. So it talks about the conservation of energy. So the first law is basically nothing but related to the conservation of energy. That is the important part. So basically the first law of thermodynamics states that energy can neither be created nor be destroyed. It means the total energy of the system remains constant. I hope this part is clear. I hope this part is clear. But how to understand this part? How you are going to change the internal energy? So let's say the initial internal energy of a particular system, whatever I have taken, is actually U1. How can I change this internal energy? Either by the work done or by heat. So let's say I have included certain amount of heat. Heat is absorbed by the system. Now the next part becomes U1 plus Q. Now let's say after this entire part, some work done is actually happening on the system. And now after that part, its internal energy becomes U2. So you can say that U2 will be equal to U1 plus Q plus W. Or you can say U2 minus U1 will be equal to Q plus W, and that's the final equation. That change in internal energy is basically equals to the whatever heat is absorbed by the system and whatever work done is on the system. Now that sign depends, like if the value is a negative, this can be negative, this can be positive, this can be negative, this can be positive. It depends in the final process what is actually happening. But you can change the internal energy with heat as well as with work done. That's why I told you that there are two modes of transfer of energy. So internal energy can be transferred in two modes. First one is heat and next one is work done. I hope this entire part is clear. Now you can say it may be possible that for example, for let's say not a cyclic process right now, let's say I can say we are talking about gases. Let's say I'm talking about the gases, the internal energy change in case of gases. And in case of gases, I know we have to include PV work done. I have to include PV work done. So it means I can say that in this particular case, del U will be equal to Q minus P del V. So that depends, we are talking about the reversible part or irreversible part, but I can include this PV work done also in this particular formula. So that's the only thing which I want to mention. Okay, now there are different type of processes for which you can define like what is going to happen in the container. Okay, so we have one question for that particular part, and question says which one of the following equation does not correctly represent the law of thermodynamics, first law of thermodynamics for the given processes involving an ideal gas. It's a very interesting question and a very important one. Assume non-expansion work is 0. So we are not talking about the non-expansion work. We are not talking about the another part of the work, because there are 2-3 more parts related to work done. There is one part which is mechanical, there is one part which is non-mechanical. So we are not assuming any non-mechanical work done which is related to the Gibbs free energy. That part we are going to discuss in the upcoming session. So just have a look at it. Now let's try to decode this entire part. We know that the change in internal energy is actually equals to Q plus W. That is your first law of thermodynamics. Okay. Now the first process is a cyclic process. What is the meaning of cyclic process? We know in that case that the initial state is actually equals to final state. That is a cyclic process. And we know, and one thing which we already know, that this delta U is basically state function. It depends upon the initial and final state. If both are same, so we can say that for cyclic process, delta U will be equal to 0. First part, delta U will be 0. If that part is true, then we can say Q plus W will be 0. If that part holds true, we can say Q will be equal to minus of W. Is it already given? Yes, it's already given. So we can say that A option is absolutely correct. Now let's try for the next part. Isochoric process. So in this case, I can say that delta U will be equal to Q plus W. So we are talking about the ideal gas. Can I say it's going to be PV work done? So delta U will be equal to Q minus P delta V. Can I write it like this? Yes, definitely. Now for isochoric process, in case of isochoric process, we know that delta V is actually equals to 0. If that holds true, I can say this entire part will be 0 and delta U will be equal to Q only. So that will be equal to Q at constant volume. Change in internal energy is only going to change the heat. So if the internal energy change is going up, it means heat is absorbed by the system at constant volume. If internal energy is decreasing or change in internal energy is negative, it means heat is released by the system at constant volume. So that is the meaning. So in this case, this particular part also holds true. This particular part also holds true. Okay. Now next part is isothermal process. Now we know that in case of ideal gas, for isothermal process, I just told you that delta U will be equal to 0. In case of ideal gas and isothermal process, because at in case of ideal gas, potential energy is independent because there is no relationship with the potential energy, no force of attraction between the ideal gas molecules. It only depends upon the temperature, and now temperature is also constant, so delta U will be 0. If that holds true, again you can say Q will be equal to minus W. Q will be equals to minus W. So that part is also true. Now last part, what is adiabatic process? What is adiabatic process? In that case, I already told you that heat change will be 0. There will be no change in the heat. So you can say that becomes Q plus W is equal to delta U. If this part is a 0, you can say W of adiabatic will be equal to change in internal energy. So in case of adiabatic processes, if the internal energy goes up, or you can say if the change in internal energy is a positive, it means work is done on the system. If that is negative, then work is done by the system. So that is the actual relationship, not this relationship. So you can say this is the incorrect part, this is the only incorrect part. I hope this portion is clear, and that's how you can determine this entire quantity for different type of relationships. Okay, just have a look at it. Okay, now let's talk about another good question. If an electric motor produced 15 kilojoule energy each second as a mechanical work and lost 2 kilojoule as a heat to the surrounding, then the change in the internal energy of the motor each second is. So it's a very easy question. So delta U will be equal to Q plus W. Okay, now electric motor produced 15 kilojoule energy each second as a mechanical work and lost. It means W is basically 15 kilojoule. W is 15 kilojoule, and I can say that Q will be minus 2 kilojoule because its work is done on the system, and Q is basically minus 2, I can say. Okay, electric motor is doing work. Okay, is a producing motor produced this much amount of energy each second as a mechanical work. It means it's again negative. Sorry, it's again negative. Work is done by the system and it's dissipating the energy in the surrounding. Okay, so delta U, you know, will be minus 15 plus minus 2, that will be minus 17 kilojoule. That will be minus 17 kilojoule. Okay. Answer is A. I hope this part is clear. I hope this part is clear. Okay, very simple question. Okay, now this question is for you guys. It's a very simple question. Calculate internal energy change for each of the following. 100 joule of work is required to compress a gas, and at same time gas releases 20 joule of heat. Again use the same part, which is a del U will be equal to Q plus W. Every value is already given. 100 joule of work is required to compress. It means work is done on the system, which is positive, and releases heat. It means Q is negative. So 100 minus 20, that will be 80. I just gave you the hint as well as the answer. So it's a very simple question. B part is a piston is compressed from a volume of 8.3 liter to 2.8 liter against a constant pressure of 2 bar. In the process, heat gained by the system is 350 joule. So heat is already given, which is plus 350. You have to calculate PV work done. So that will be minus P external V2 minus V1. So just have you have to put the value. I have given you the hint. And the last part, a piston expands against 180 m of pressure from 11.2 liter to 29.2 liter. In a process, 2820 joule of heat is absorbed. Q is now positive, and in this case, you again have to calculate PV work done. So this I am giving you as a homework. Just try to solve this question and let me know the final answer in the comment box. Okay. In the next class, I'll try to make sure that we have the correct answers on both the sides. Okay. So this is the basic part, again related to the first law of thermodynamics. Very basic question, very interesting one. You can do it by yourself. Okay. Now, the last part which remains is basically the concept of enthalpy. So why we have introduced the concept of enthalpy? What is the need? We know in previous case we were talking about the container, like whatever we are talking about the constant pressure process. Always remember, in this case we discussed about the process of constant volume. We discussed about the process related to constant volume. Constant volume processes, whenever we talk about the constant volume processes, always remember they always occur in closed container. They always occur in the closed container. But in general life, whenever we talk about the chemical reactions, because we are talking about the chemical reactions only, PV work done is basically gas is present in the container, it is expanding, it is compressing. But generally, when we talk about the reactions, we don't know what is internal energy is going to change of the system when the reaction is happening, because every time we generally used to do the reactions in open vessels, either in the beaker or in the test tubes. So generally, we know in general, most of the reactions occur in open vessel or container. It can be your test tube, it can be anything. But the main thing is, in that case, constant volume is not possible under these conditions. So always remember, constant volume is not at all possible under these conditions. So this is the first part. So we can say that the entire process which is present in the open container, it is happening, but we can say reaction is happening under constant external pressure. But we can say that whatever reaction is happening is always under a constant atmospheric pressure. That part is true. So you can say whatever part we have discussed in the previous session, we were talking about the constant volume and constant temperature. We were talking about the constant volume and constant temperature. Now it's time to discuss about the concept of enthalpy, which is for constant pressure as well as constant temperature. So generally in this case, we are talking about the heat change or the energy change which is happening under constant pressure generally. So we talk about the constant pressure part. So it is the heat contented in the system at constant pressure, because most of the reactions are happening in this way. That's why enthalpy is a very useful. And you know, in case of thermochemistry, in case of even periodic classification, we generally talks about the enthalpy term much more. We doesn't talk about the internal energy. We talks about the ionization enthalpy, we talk about the electron gain enthalpy, we talk about the lattice enthalpy, we talk about the hydration enthalpy, because every reaction is happening in open container which has a constant external pressure. So whatever heat is changing in that case, that is basically your enthalpy part. I hope this part is clear. It is represented by symbol which is H. Again, it's a state function definitely, and it is an extensive property. It is an extensive property. Now it is the sum of the internal energy and PV work done of the system. This is the most important part. So I can say that this enthalpy is basically the summation of internal energy as well as PV work done, because the entire part is occurring at a constant pressure, external pressure. It means internal energy is always there, and PV work done, I have to include the PV work done also. So that is the basic idea related to the entire part of enthalpy. I hope this portion is clear. So mathematically you can say H is actually equals to U plus PV. Now like U, absolute value of H cannot be determined very easily, but we are more concerned about the determination of delta H. we are more concerned about the determination of delta H, which is H2 minus H1. So I can say from this particular part that delta H will be equal to delta U plus delta PV. Can I say this? Yes, definitely, definitely true. I can say this, that this part is going to be hold true. So for example, if I talk about the H1, that will be basically U1 plus whatever part I have taken, P1 V1. H2 will be U2 plus P2 V2. Let's say. So we can say that delta H, which is H2 minus H1, will be U2 minus U1, which is delta U plus a delta of PV, P2 V2 minus P1 V1. So that is the basic part. We have derived this particular formula also. There is no need to understand this entire part, but I have just given you what is the basic relationship in this particular case. Okay. Now we know that we have one formula which is related to the change in enthalpy. Change in enthalpy. Okay. Can I expand this formula? Yes, very easily. So del H will be equal to del U plus P del V plus V del P. Now this internal energy change, enthalpy change is happening at constant pressure. We know the entire part we are talking about at constant pressure. If this holds true, if we are talking about the constant pressure part, then we can say this entire part will be 0. So the final equation becomes delta H will be equal to del U plus P del V. I hope this part is clear. I hope this part is clear. Now we know that according to first law of thermodynamics, this entire part will be equal to Q plus W. Okay. Now in case of gases, we know that this W is actually equals to minus P delta V. That is the interesting part. So you can say it becomes delta H will be equal to Q plus minus P delta V plus P delta V. This entire part is going to cancel out, and from that part you can say delta H will be Q at constant pressure. I hope this part is clear. So whatever heat is changing at constant pressure is basically the change in enthalpy. So now always remember two equations, that delta U corresponds to Q at constant volume. This part also we have determined. And next part is the delta H will be equal to Q at constant pressure. So whatever change in enthalpy is happening, if it is increasing, it means heat is absorbed by the system at constant pressure. If this change is negative, it means heat is released by the system at constant pressure. So that is the meaning. Always remember these two parts. They are going to be very, very important for heat capacity calculation. Okay. So this is the equation which you can see. This is the very basic analysis related to the entire part. Is there any other formula? Can we calculate other formulations of delta H? So yes, we can calculate the other formulations of H. So we know that H is basically U plus PV. A change in enthalpy arises due to change in internal energy and change in the product of a PV. So this part is already true. This part is already true. Okay. Now we can say that we know that delta H will be equal to delta U plus delta of PV. That part is true. That part is true. Now, how can we say? Okay, let's try to figure out. So we know that P initial, V initial. So I am applying for ideal gas. Just like the internal energy change. Now let's try to apply for ideal gas. Okay, let's say P initial, V initial will be equal to nRT, or I can say N of gaseous initial RT, constant temperature, at constant temperature. Okay, so this is the equation. We know that P final, V final will be equal to Ng final RT. So I can say from this particular part that delta in PV is basically equals to P final, V final minus P initial, V initial. or I can say that will be equal to Ng final minus Ng initial multiplied by RT, or I can say that will be delta of Ng RT. So can I put this equation here? Yes, definitely. I can say that delta H will be equal to delta U plus delta Ng RT. But what is the meaning of this delta Ng? Always remember that this delta Ng is basically difference between gaseous moles of product and reactant. That's the basic part. So if the moles are changing, then you can consider this part. If temperature is changing, again you can say it will be T2 minus T1 again. So you can simply put this as nRT. So nR delta T. So if that is for if first condition is constant temperature, but moles are variable. Moles are variable, then you can use this equation. If that doesn't holds true, then you can say delta H will be equal to delta U plus nR delta T if moles are constant but temperature is variable. So according to your need, you can change these equations. Okay, so that is one of the part. This is the most important equation. Generally, this equation is pretty much used in case of ideal gases. Delta H is equal to delta U plus delta Ng RT. Okay, now we have one question which is related to this part. For which of the following reactions delta H is less than delta U? So we know that delta H is actually equals to delta U plus delta Ng RT. Now let's say if this delta Ng is actually positive, it means positive. So I can say delta H will be more than delta U. If this delta Ng actually becomes equal to 0, then you can say delta H will be equal to delta U. And when this delta Ng is less than 0, or you can say it is actually negative, then you can say that delta H will be less than delta U. This is the only condition which is required in the question. So I can say we have a solid. So in this case, delta Ng will be product 1 minus 0. That will be 1 because only one gaseous product is there, no gaseous reactant. In this case, you can say delta Ng will be equal to 2 minus gaseous 4. So that will be minus 2. So I guess this is the answer. But otherwise, if we can say in this particular case, delta Ng will be 2 plus 1, 3 minus 2, which is positive. So no, not this case. Delta Ng in this case, again same, only one gaseous reactant, no gaseous, only one gaseous product, no gaseous reactant. So this is again positive 1. So 1, 1, 1, but this part is negative. So negative means delta H will be less than delta U. So that will be the correct answer. I hope this part is clear. So we have calculated the entire part. Next question, the enthalpy change for the reaction of 50 ml of ethylene with 50 ml of H2 at 1.5 atm pressure is this. What is the value of delta U? So I am giving you this question for homework. Again, apply the same equation and try to calculate the final answer. Okay, so we have completed almost everything related to the first law of thermodynamics as well as different formulations. And in the next class, we are going to discuss the further analysis, the extension part of your first law of thermodynamics as well as the concept of heat capacity, molar heat capacity at constant volume as well as constant pressure. That part also we are going to discuss. Then we are going to discuss about the adiabatic processes. I hope this entire session is clear to everyone. I hope everyone enjoyed this session and learned something new from this session. Remaining part we will discuss in the next part. Okay, so that's all from my side. Thank you so much.